Hello there, I've received a question about this problem, which is 8.2, number 16 in the study plan. Who knows where it would be in the actual homework assignment you've got? So it says, according to a study conducted by a statistical organization, the proportion of Americans who are satisfied with the way things are going in their lives is 0.84, because we're going to do an example. We're not going to do the actual problem that I have listed here, but an example that's like it. All right, suppose that a random sample of 107 Americans is obtained. Complete parts A through C. Okay, so part A is describe the sampling distribution of p hat. Well, remember from the central limit theorem in the notes that if we have a random sample with independence and a large sample and a big population, then we're doing well and we can apply the central limit theorem for sampling proportions to this problem, which we have all of these things. So let me write that up. All right, so I typed this up, and I just wanted to make a note that the three conditions that we need in order to apply the central limit theorem are all met for proportions, theorem for proportions, right? Or sample proportions, I should say. All right, now what are those conditions? Number one, it said it had to be a random independent sample. Well, if you look at the problem, it says that it's a random sample of 107 Americans. So that gets us our randomness. Then it says that it needs to be a large sample. So we need n times p times 1 minus p to be greater than 10. So n times p times 1 minus p is 107 times 0.84 times 1 minus 0.84. So if I grab the calculator, I take 107 times 0.84 times parentheses 1 minus 0.84. And hope that this is bigger than 10, and it is. It's 14.3808. So that is larger than 10. So we have that condition met. Great. Then we also need it to be a large population, but this is going to be kind of a hand-waving thing. Well, of course it is. Our sample was collected without replacement, one assumes, because when they do a survey like this, they don't want to call the same household. So if you look at those 107 people, those 107 people they called are far less than 1.05 times all Americans, right? Or the number of all Americans, I should say. Capital N is your population size. So the number of all Americans, which is your population size, is much larger than 107. All right, now that we've met those three conditions, that means that we can apply the central limit theorem for sampling proportions, which means we need to know the shape, but we know that it's normal because of the conditions above being met. So we know the shape is normal because the conditions above are met. Then we need to know the center and the spread. Now the center is mu p hat, which would be equal to p. And in our case, that will be our population proportion, which is 0.84. So that would be our mu. Oops, wrong. That went to the central limit theorem. So that would be our mu p hat. Mu p hat is equal to p, which in this case is 0.84. All right, now we need the standard error. That will be our spread, right? So the center is mu p hat, oops, which is equal to p. Yep, I know. My computer is not liking me. All right, then I need the standard error. So the standard error is going to be this sigma p hat, which is the square root of p times 1 minus p over n. So this is going to be my standard error. That will be the spread. Okay, so that would be equal to, now we got to find this. This is equal to the big square root. Now p for us was 0.84 times 1 minus 0.84, and we're going to divide all that by n, which in our case was 107. So let me grab a calculator. And I want to take a square root, which is second x squared, and then you can actually tell it to do a fraction right now, or you can just type it. So we want p times 1 minus p, so 0.84 times, well, actually you don't even need a times, you can just do parentheses, 1 minus 0.84, close your parentheses. Oh, except I need a 4 in there. parentheses 1 minus 0.84, close parentheses, divide that by 107, enter. And there you have it. It's 0.03544. Now, if you have a newer calculator, you can actually do second square root, then hit the alpha F1 button, right, which is the y equals button. See how it's F1? And you can choose the fraction menu, which is numerator over denominator, n over d, number 1. So I hit number 1, and it actually makes a fraction that looks like what it looks like on the paper. It's not liking my 4s. There we go, parentheses, 1 minus 0.84. There we go. Arrow down, so use your arrow keys, and then hit 107, enter. So if you have a TI-84 with the newer operating system, you can actually do that by hitting the alpha F1 key. You'll get the same answer, but it looks more like what it looks like on paper. So now we know it's 0.035441. So that's an approximation. 0.035441. Or was it 411? 441. We're good. All right, there's our shape, there's our center, there's our spread. So let's go back to the problem for a second. And sure enough, that's what it wants for the beginning part. It wants the shape, it wants the center, it wants the spread, and sure enough, we get 0.035. Notice it's proving n times p times 1 minus p is greater than 10, which proves our normality and all of that good stuff. It's got a normal distribution, mu 0.84, sigma 0.035, just like we said. Now it says, using that distribution, what is the probability that at least 88 Americans in the sample are satisfied with their lives? Now you notice it's asking about the probability here. So the probability that at least 88 Americans. So let's look at the 8.2 decision matrix. And we can see that it's asking for, we want to know a probability right here. So we're going to need to know a p hat in order to be able to use normal CDF. That's our goal. So we know where the center of the curve is because we said so. It was 0.84. And we know that the spread is 0.035. Right? Because we said it's normally distributed and all that good stuff. So this is part A right here. So for part B, we actually want to be able to use the fact that it's normal and apply the decision matrix. Right? Use normality and the 8.2 decision matrix to find the probability. All right, well, like most normality probabilities, we probably want to draw a graph for this. So let me go draw a normal graph. I'll be right back. All right, so I drew a normal distribution and I put P, which was my mu, of 0.84 in the middle. And then you'll notice that it's talking about to find the probability of at least 88 Americans believing blah, 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 blah. So there's a problem right there because 88 is not a p hat. 88 is an x value. But if you look at the decision matrix, we need to have a p hat. So you're going to have to use the formula for p hat, which is x over n, to find the p hat value that you can use on this curve, which, as you can see, I've already found it, but I'm going to prove it to you. So p hat is x over n, which is, and the x that they gave you is 88, and n we already knew was 107. So if you take 88 and divide it by 107, you get about 0.8224, which is where I'm coming up with that number when you look at the graph. That's your p hat value. Right, so p hat is where this vertical bar is over here. And it said at least 88 Americans, which means 88 Americans or more, right? So at least 88. All right, now how do we find this area? Right, now we've drawn it, we've labeled it, everything's great. To find that area, the probability that p hat is at least 88. So p hat is greater than or equal to 0.8224. Right? That means, so the number is greater than 88, which means that the p hat is greater than or equal to 0.8224 is equal to normal CDF. And then we want to go left, comma, right, comma, p, comma, standard error of p. So if we look at the left-hand edge of what we shaded, the left-hand edge is 0.8224. Now you could put in 0.8224, but that loses some accuracy. So you're better off just doing the number, which was 88 over 107, comma, And then we know the right-hand edge is 1e99. We've run into that before. It's the forever because it's going forever to the right side. P was 0.84. And then the square root of 0.84 times 1 minus 0.84 divided by n, which in our case was 107. So if we can put all of that into a calculator, we'll be good and we'll know our answer. All right, well, and this will be an approximation. Oops. There we go. All right, so I'm going to go grab a calculator. I'm going to clear this out. I'm going to go to my distribution menu. I'm going to pick normal CDF, which is number 2. The left was 88 divided by 107. The right is 1E, which is above your comma button. It's the double E for scientific notation, 99. P was 0.84. And square root of 0.84 times, oopsie, left parentheses, times 1 minus 0.84. Oh, I lost my 4 again. That keeps happening to me. My button doesn't like me. I'm going to insert because I don't want to lose the rest of what I've typed here. So 0.84, 1 minus 0.84 divided by n, which was 107. There should be 2 sets of parentheses, one for the 1 minus 0.84 and then the bigger one to start the square root and end the square root. Then I'm going to go down to paste and press enter. And then I press enter. And I get 0.68996, which if you round to 4 decimal places, that 6 would round the 99 up and become 0.6900, right? Right? Let me go back and double check that. Yeah, 6900. Now, if they want less accuracy than that, then we can use the decimal approximations for some of these things. But let's see what they do when they look at the problem. And that'll give us a hint of how much decimal approximation we want to do. So, yeah, there's the 0.82. So they really rounded that to 0.82 instead of 0.8224. We kept more accuracy. So by doing 88 over 107. So if they want to do 0.82, which is fine, then we can do that too. So we'll go to second distribution, pick number 2. If they want to keep it that inaccurate, we can do 0.82, 1E99, and then 0.84, and then down here we could do 0.0035 for our standard error, and then paste that. Oops, I lost my decimal point. You can see it's 0.82, which is not what I meant to do, my fault. So I got to go back in there and make that a decimal point. Sorry about that. And right here, and I'm going to insert second INS and put in a decimal point. There we go. In general, if you get a 0 or a 1 on one of these problems, you know you've done something wrong. There, and that's closer to their answer, so 0.716. Yep, and that's what they're getting. So they're using the rounded values, which is fine. So then just use the rounded values when you do the problem yourself. But realize if you're working on like worksheets or paper pencil packets or whatever projects, you can use more accuracy. That won't bother me. But apparently they only want a couple decimal places of accuracy here. So that's fine. Okay. So now for the part C. So let me type this up real quick. There we have it. So it's actually closer to 0.69, but if you round everything, then it'll be about 0.7161. All right, part C wants to know the probability that, using the distribution for part A, what is the probability that 82 or fewer? So that's going to be on the left side. So I'm going to have to convert 82 to a p hat. Let me go draw that graph one sec. All right, so for part C, they wanted less than 82. So you have to go back to the formula for p hat, which is in the decision matrix. It's x over n. So you take 82 divided by 107, you get about 0.766, right? And then you want to be less than that. So you want to go 0.766 and less than. To find that, you'll need normal CDF from left to right. But in this case, the left-hand edge is negative 1E99 to 0.766. So let's do that. So we're going to go from normal CDF. We're going to take negative 1E99 Then we're going to go to 0.766, and then 0.84 and 0.035 because apparently that's all the accuracy they want on these problems. And that gets us 0.0172. So let's see how that jives with their answer. Oh, they've got, oh, they rounded to 7.7. All right. Well, if we round to 7.7, yeah, because they're only doing 2 decimal places and I did 3. It's my natural inclination to do more decimal places, not less. So if I change that to 7.7 in here, then let's see how this works. Yep, there we go. And then we get 0.0228, 0.2275, just like they expect, right? 'Cause, yep, 0.228, just like they think. Okay, so let me type that up. There we have it. So if you use their method, you'll come up with about 0.0228. If you do use the fraction and the square roots and all of that, you'll actually get a more accurate answer, which is 0.01886. But apparently MyStatLab doesn't want that much accuracy. But either one should work for by hand stuff if you're doing, worksheets and such, unless I specifically ask for more decimal places for that standard error in the back. All right, I hope that helps with that problem, and I'll see you back here for more tutorials.